Okay, welcome everyone. This is Math 7502. This is our practical session of week 7. So this evening we will be going over the quiz that you did, and that was your second quiz of the Math 7502 course. And so I believe we've got 10 questions. We'll first hear from Walla, who will cover the first 7 questions, and then I'll come in and I'll talk to you about questions 8 through 10. And then if we have any time, I'll say a few words about polynomials, because you are in this course later going to learn about eigenvalues and eigenvectors, apparently very soon. So that will be appropriate. Okay, Walla, are you ready?
Yeah.
All right. Welcome, Walla. You might want this chair a little taller.
Yeah, thank you. Yeah, hi everybody. We will start to solve some questions from quiz 2. Let's start with question 1. Consider the vectors v1, v2, and v3. Let the 3 times 3 matrix A have columns v1, v2, and v3. That is, A is a matrix v1, v2, and v3. In number 1, they ask you, do the vectors v1, v2, v3 constitute a set of orthogonal vectors? They give you 3 vectors at the beginning. And question 1, we have 3 vectors. v1 is -1, 0, and -1 transpose. We have v2 equal 0, -1, and 1 transpose. And we have v3 equal 0, 1, and 1 transpose. In number 1, they ask you if these vectors are consist an orthogonal matrix. To be sure that these vectors consist an orthogonal matrix, we need to find an inner product between any 2 vectors. If the inner products between any 2 vectors from the matrix A equals 0, then we can say that these 3 vectors constitute an orthogonal matrix. Let's try to find the inner product between v1 transpose times v2. v1 transpose times v2. v1 transpose is -1, 0, and -1. Multiply with 0, -1, and 1. We need to find the inner product between v1 transpose and v2. -1 times 0 is 0. 0 times -1 also is 0. -1 times 1 equal -1. Because the answer is not equal to 0, we can say that v1, v2, and v3 does not consist an orthogonal matrix. So the answer is no. Why? Because when we try to find an inner product between v1 transpose and v2, we get the answer is -1, which is not equivalent to 0. So we can say that the answer is no in part 1. It's clear for you? Okay. Okay. Let's move to part 2. In part 2, they ask, are the vectors v2 and v3 orthogonal? We need to test that if v2 and v3 are orthogonal. To test that, we need to find v2 transpose times v3. Number 2, they ask if v2 and v3 are orthogonal. To test that, we need to find the multiplication between v2 transpose times v3, the inner product between v2 transpose and v3. v2 transpose, it's equal 0, -1, and 1. Multiply with v3, which is 0, 1, and 1. If you try to find an inner product between v2 transpose and v3, you will get 0 times 0 is 0, -1 times 1, -1, plus 1 times 1 equal 1. So -1 plus 1 equal 0. So v2 and v3 are orthogonal. Why? Because the answer is 0. So the answer here is Yes, why? Because when we try to find an inner product between V2 transpose and V3, we get the answer is 0. Because the answer here is 0, we said that V2 and V3 are orthogonal. This is for part 2. It's a direct question. Okay. And part 3, they ask, execute the Gram-Smith procedure on the vectors V1, V2, and V3 in this order. Present the output as columns of an orthogonal matrix Q. We need to apply Gram-Smith matrix at the beginning. Be sure that we have V1, V2, V3 in this order. And we need to put the result in a matrix Q. Let's try to find the Gram-Smith. Question 3. At the beginning, we need to know what is the Gram-Smith set. The Gram-Smith said that to find the Qi tilde, this is equal to Vi minus Q1 transpose times Vi. All of these multiply with Q1 until you reach the Qi minus 1 transpose times Vi. All of these multiply with the Qi minus 1. And remember that we have V1 is the vector minus 1, 0, minus 1 transpose. V2 is 0, minus 1, and 1 transpose. And V3 is 0, 1, and 1 transpose. Let's try to find the Q1 tilde. To find the Q1 tilde, just substitute in Gram-Smith algorithm. Q1 tilde equal V1. And V1 here is equal minus 1, 0, minus 1 transpose. And this is not equal to 0. According to Gram-Smith, if Q1 tilde not equal to 0, so we need to continue. So this vector is independent. Now we need to find the value of the Q1. To find the value of the Q1, this is equal Q1 tilde divided by the norm of Q1 tilde. So we need to divide every term from the Q1 tilde by the norm of the Q1 tilde. Here we have the vector minus 1, 0, minus 1 transpose. We need to divide by the norm of the Q1 tilde. To find the norm, this is equal to square root of minus 1 squared plus 0 squared plus minus 1 squared. So minus 1 to power 2 plus 0 to power 2 plus minus 1 to power 2. So this is equal, we have this vector minus 1, 0, minus 1 transpose divided by square root of 2. So we need to divide minus 1 over square root of 2. We need to divide 0 over square root of 2 and minus 1 over square root of 2. So this is the value of the Q1. So Q1 here equal minus 1, 0, and minus 1 over square root of 2, 0, and minus 1 over square root of 2 transpose. So this is the value of Q1. Now let's try to find the Q2 tilde. To find the Q2 tilde, we need to apply Gram-Smith again. Q2 tilde, this is equal V2 minus Q1 transpose in a product with V2, and all of these multiply with Q1. What's here? V2 is equal to 0, minus 1, and 1 transpose. This is the value of V2 minus, we need to find an inner product between Q1 tilde, Q1 transpose and V2. Q1 transpose is minus 1 over square root of 2, 0, and minus 1 over square root of 2. This is multiplied with V2, which equal to 0, minus 1, and 1. And all of these multiply with Q1, which equal minus 1 over square root of 2, 0, minus 1 over square root of 2. Now we need just to simplify. We need at the beginning to find an inner product between Q1 transpose and V2. Then we need to simplify. This is equal to 0, minus 1, 1 transpose minus. Let's try to find an inner product minus 1 over square root of 2 multiplied with 0. This is 0. 0 times minus 1 also is 0. Minus 1 over square root of 2 multiplied with 1 is minus 1 over square root of 2. Here we have minus 1 over square root of 2. This is multiplied with minus 1 over square root of 2, 0, and minus 1 over square root of 2. Transpose. Now we need to simplify. We need to multiply each term from 1 over here, from Q1, with minus 1 over square root of 2. Then we need to subtract V1 from this value. So here we have Q2 tilde equal 0, minus 1, and 1. Transpose minus 1 over square root of 2 multiplied with minus 1 over square root of 2, 0 minus 1 over square root of 2 transpose. This is equal to 0 minus 1, 1 transpose minus, let's try to multiply, minus 1 over square root of 2 multiplied with minus 1 over square root of 2. This is equal 1 over 2. This is 1 over 2. Minus 1 over square root of 2 multiplied with 0. This is 0, and minus 1 over square root of 2 multiplied with minus 1 over square root of 2. This is also a half, and this is here transpose. Now we need just to subtract 0 minus a half. This is a half, sorry, minus a half, minus 1 minus 0. This is minus 1. 1 minus a half. This is equal a half transpose. This is the value of Q2 tilde. Because the value of Q2 tilde not equal to 0, so we need to continue. And we need to find the value of Q2. To find the value of Q2, we need to find Q2 tilde divided by the norm of Q2 tilde. The vector of Q2 tilde equal minus a half, minus 1 and a half transpose, divided by the norm of Q2 tilde. And the norm here is equal to square root of minus a half to power 2 plus minus 1 to power 2 plus a half to power 2. This is equal, here we have the same vector, minus a half, minus 1 and half to power to transpose, divided by, if you try to simplify this one, this is will give you square root of 6 over 4, square root of 6 over 4. If you need to simplify, it's equal square root of 3 over 2. By divide each term here by 2. This is equal square root of 3 over 2. So the value of Q2 equal minus a half divided by square root of 3 over 2, which equal minus 1 over square root of 6, minus 1 divided by square root of 3 over 2. This is equal minus square root of 2 over 3, and a half divided by square root of 3 over 2. This is equal also 1 over square root of 6. So this is the value of Q2. We need the value of Q1, Q2, and Q3 to write the matrix Q. So we need to find also the value of Q3, and at the beginning we need to find the value of Q3 tilde by applying Gram-Smith again. To find the value of Q3 tilde, the value of Q3 tilde equal V3 minus Q1 transpose, another product with V3, and all of these multiply with Q1 minus Q2 transpose, another product with V3, and all of these multiply with Q2. Let's try here, substitute the value of V3, the value of Q1, the value of Q2, and find the value of Q3 tilde. So the value of Q3 tilde equal V3, which equal to 0, 1, 1 transpose, minus, we need to find here an inner product between Q1 transpose and V3. The value of Q1 transpose, we find it at the beginning, the value of Q1, which equal to minus 1 over the square root of 2, 0, and minus 1 over the square root of 2. This is inner product with 0, 1, and 1. Okay? This is multiplied with the Q1, which equal to minus 1 over square root of 2, 0, minus 1 over square root of 2 transpose, minus Q2 transpose, which equal to minus 1 over square root of 6, minus 1 over square root of 6, minus square root of 2 over 3, and 1 over square root of 6. This is inner product with the value of V3, which equal to 0, 1, 1. And all of these multiply with the value of Q2, which equal to minus 1 over square root of 6, minus square root of 2 over 3, and 1 over square root of 6. So at the beginning, we need to find an inner product of Q1 transpose times V3, and we need to find the value of Q2 transpose times V3, okay? Then we need to simplify, okay? Now, if you multiply here, minus 1 over square root of 2 with 0, this is 0. 0 times 1 also is 0. Minus 1 over square root of 2 with 1. So from here, just we can get minus 1 over square root of 2. And from here, if we multiply minus 1 over square root of 6 with 0, this is 0, and minus square root of 2 over 3 times 1, this is equal minus square root of 2 over 3. And if we multiply 1 over square root of 6 times 1, this is equal 1 over square root of 6. If you multiply, if you simplify, minus square root of 2 over 3 plus 1 over square root of 6, you will get minus 1 over square root of 6. So let's try to make it tidy. So the value of Q2, the value of Q3 tilde equal to 0, 1, 1 transpose minus 1 over square root of 2 multiply with 0, 1, and 1 transpose minus 1 over square root of 6 multiply with, sorry. Okay. So the value of Q3 tilde equal 0, 1, 1 transpose minus 1 over square root of 2 multiply with minus 1 over square root of 2, 0, minus 1 over square root of 2 transpose minus 1 over square root of 6 multiply with minus 1 over square root of 6 minus square root of 2 over 3 and 1 over square root of 6, okay? If you try to multiply these together and try to multiply minus 1 over square root of 6 with this vector, you will get Q3 tilde equal 0, 1, 1 transpose minus half, 0, half transpose minus 1 over 6, 1 over 3, and 1 over 6 also transpose. Now just you need to find the value of Q3 tilde. So the value of Q3 tilde equal 0 minus 1 over 2 minus 1 over 6. This will give you minus 2 over 3. 1 minus 0 minus 1 over 3. This is equal 2 over 3. And 1 minus a half, 1 minus a half minus 1 over 6. This will give you also 2 over 3 transpose. And the value of Q3 tilde also not equal to 0. So we need to find the value of Q3, the same thing, the value of Q3 equal Q3 tilde divided by the norm of Q3. This is equal minus 2 over 3, this vector, 2 over 3, and 2 over 3 divided by square root of minus 2 over 3 to power 2 plus 2 over 3 to power 2 plus 2 over 3 also to power 2. Okay? If you try to simplify, this is will give you minus 2 over 3, 2 over 3, and 2 over 3 transpose divided by 2 over square root of 3. So we need to divide each terms here in Q3 tilde by 2 over square root of 3 to find the value of Q3. You will get that Q3 equal minus 1 over square root of 3, 1 over square root of 3, and 1 over square root of 3 transpose. So now we found the value of Q1, Q2, and Q3. Now we can write the matrix Q. The matrix Q with the 3 vectors. The first vector is Q1, the second vector is Q2, and the third vector is Q3. The value of Q1 is minus 1 over square root of 2, 0, and minus 1 over square root of 2. The value of Q2 is minus 1 over square root of 6, minus square root of 2 over 3, and 1 over square root of 6. And the value of Q3, this is this one. This is minus 1 over square root of 3, 1 over square root of 3, and 1 over square root of 3. So this is the matrix Q. Okay, because at the end of the question, they ask you find the matrix Q. Okay, 1 over 6, 1 over 3, 1 over 6. The last 1 over 6 should be minus yes, here minus 1 over, yes, this is minus, it's positive, minus, yeah, this is minus, yes, correct. Yeah, you asked about this one, yes, it's correct. So this is the value of matrix Q. Okay. Is there any question? Okay. Let's move to question 4. In question 4, they ask determine Q inverse. They ask you to find the value of Q inverse. In question 4, they ask to find the value of the Q inverse. If you look here, we found the value of Q. We found this value of the Q, which is an orthogonal matrix. Because the Q is an orthogonal matrix, the Q inverse equal Q transpose. Because Q is an orthogonal matrix, so Q inverse equal to Q transpose. Okay, so because they ask you to find Q inverse, and Q here is an orthogonal matrix, so Q inverse is the same as Q transpose. This is the solution of part 4. Okay. In part 5, they ask, what is the null space of the matrix A? We need to find the null space of matrix A. We need to find the null space. Okay. After we applied the Graham-Smith, we found that the values of Q1, Q2, and Q3 are linearly independent. So if they have some of vectors which are linearly independent, so it has just only one null space which equal to 0. So the null space of this matrix just 0, 0, 0 transpose. Because we have, since we see from Graham-Smith algorithm, the vectors are linearly independent. So the null space equal just 0, 0, 0 transpose. In general, if you have vectors which are linearly independent, so just you will get that the null space all the time is 0, 0, or 0's null space. All the time you will get 0's null space. In number 6, what is the rank of the matrix A? We need to find the rank of this matrix. we need to find the rank of matrix A. Matrix A is a square matrix. Since the matrix A is a square matrix and consists of linearly independent columns, so the ranks of this matrix equal the numbers of vectors in this matrix. So the ranks of matrix A here is equal the numbers of vectors, and here we have just 3 linearly independent vectors. So the ranks of this matrix equal 3, because A is a squared matrix with linearly independent columns. So the rank of this matrix equal the number of linearly independent columns, and here we have just 3, so the rank equal 3. So answer here is 3. Okay. If you calculate the matrix Q correctly, so you will get the answer correctly. Okay. In number 7, they asked, are the vectors v1, v2, and v3 a basis for R3? Number 7, or they ask you if v1, v2, v3 consist a basis in R3. If these 3 vectors consist a basis in R3, the answer is yes. Why? Because this vector span in R3. This is the first thing. And the second thing, these vectors are linearly independent. So yes, it's basis in R3. So just you need to say yes. Why? Because the vectors span in R3 and they are also linearly independent. Okay, so this is the answer of question 7. Is it clear for you? Yeah, is there any question? Okay. Now let's continue with some question 8, 9, and 10.
Righto, thank you, Walla. That went a little bit quicker than I expected. So I guess I might be speaking rather slowly. We'll see. Okay, so the first one I'm going to go over, I have written right here, but let me get organized. You can read what I've got. So, Walla has the printout, but I don't have the printout here. It's not, well, I guess, okay, I've kind of written an abbreviated form of what's written there, but maybe it's better if I just show you the problems we'll look at. Thanks, Walla. Okay. I think I pretty much am organized. Okay, so our first one says, now execute the Gram-Schmidt procedure on the vectors v3, v2, v1 in that order. Present the output as columns of an orthogonal matrix M. So I've kind of taken the liberty of renaming letters here. So sorry about that. But I mean, the vectors that you're given are up here at the top. Okay, and so, so we're doing this in reverse order. We're basically calling this the first vector, this v3, and then v2 is the second, and v1 is the third vector in the procedure. Okay, so now I'll go to what I've written. So I've basically got run it on v3, v2, v1, and I'm going to just rename them straight away, right? I'm just going to call a1 the first one that we'll work with, which is v3 here. And likewise a2 and a3, okay? And so now you'll see I've got the formula here that we need to run written as it pertains to these three, A1, A2, A3. Okay, and then obviously, once we calculate this, we take a norm and we divide by the norm. Okay, so you can see my letters may be a little bit different to what Walla used. So Walla had a tilde over here, right? So don't get confused by that. I'm doing the same procedure. So now I put a hat on them when they're unit vectors, okay? And inside the bracket there, I just have a dot product. Whereas you often do that with a matrix product, right? It's the same thing though. Okay, so let's begin this. Now, first, let's note where our sum stops, right? Because if we put in I equals 1, so I'll write that to start with, I equals 1. And I can do that because I plan to go a little bit slowly. I've only got 3 questions to go over, and they're fairly easy. But you may not agree because you did the quiz, right? Okay, so if we've only got I equals 1 here, that means that this sum stops before it starts. Okay, so there's nothing in the sum. So in that case, Q1 is equal to A1, and then we can just copy it down right there. So we have 0, 1, 1. Okay, now all we have to do is calculate the norm of that vector and divide by the norm, and then we have Q1 hat. Okay, so we can see that the square root of 0 plus 1 squared plus 1 squared is root 2. And so we're dividing by root 2. So straight away we can write down Q1 hat is 1 on root 2, 0, 1, 1. I like to keep the third part of it on the outside because I don't like rewriting it over and over. Okay, so now that we've got that, we're ready to look at I equals 2. So I'll draw a line here. I'm ready to look at I equals 2, so I'll put I equals 2. Okay, so we use the formula now, but in this formula, we stop with the top being 2 minus 1, which is 1. So there's exactly one thing in that sum. Okay, so we have Q2 is equal to A2 minus, and now we've only got one thing, remember, so I'll put it there. And then we're summing over the K, so that would mean that that K is 1. Are we still on? Yep, okay. Right, and it's got a hat on it, okay, and in here as well, Q1 with a hat on it, and then we have A2, right, because the I is equal to 2. Okay, so now that I've put that in, now I just need to substitute and calculate. Okay, so subbing in the A2, let's see, it's right there. So we have 0, minus 1, 1. And then we're subtracting a dot product, so I'll leave plenty of space. And then over here, I'll put in the Q1 hat, which we calculated as 1 over root 2, 0, 1, 1, just right there. All right, so now let's see, A2 is this one. So let's put it in 0, minus 1, 1. And then we're taking the dot product, 0, 1, 1. With a 1 on root 2 in the front. Okay, so that scalar can come all the way out here if you want. And so this in brackets here, that's a scalar, all right? So let's just calculate it. 0 times 0 is 0. Minus 1 times 1 is minus 1. 1 times 1 is plus 1. So the sum of those, considering that we pull the scalar out the front, okay, that's just adds up to 0. Okay, so we find out that this is just 0, minus 1, 1, and then minus 0. Okay, so, and of course, that's the 0 vector because the scalar is 0, and we multiply in by this vector, and we get the 0 vector there. Okay, so it's compatible. And now that we've got Q2, which Walla wrote with a hat on it, I think, sorry, with a tilde on the top, now we need to take the norm and divide by the norm. But again, we can see that that norm is the square root of 2. Okay, so then we see that Q2 with the hat on it, the unit vector is 1 on root 2, 0, minus 1, 1. Okay, great. So we've got the first 2 columns, namely these two, 1 and 2, of our orthogonal matrix uppercase Q. So now when I equals 3, this is our last case, let's write out the formula. So we would have, sorry, that's a 3, isn't it? Not a 2. Okay, we have Q subscript 3 equals A subscript 3 minus the sum from K equals 1 to 3 minus 1 is 2. So this is two things. And now inside we have I subscript 3 dot QK hat, QK hat outside. Okay, so now I can go and put the things in the sum, K equals 1 and K equals 2. So A3 minus A3 dot Q1 hat, scalar product, Q1 hat, and then minus A3 dot Q2 hat, and then all times Q2 hat. Okay, good. Now I can sub things in and calculate. So A3, we have it right up here, minus 1, 0, minus 1. Okay, so I'll put that in, minus 1, 0, minus 1. And then I wonder, is it a bit risky maybe to calculate the dot products in our head to save some writing? I don't know, let's see. Yeah, possibly, we better be careful. Okay, so let's put this in. Minus 1, 0, minus 1. And then dot Q1 hat, 0, 1, 1. And then we'll put that scalar 1 on root 2 out the front. And then we have 1 on root 2, 0, 1, 1, which is Q1 hat. And then we come to our other term. So A3, which is minus 1, 0, minus 1 again, and then we're dotting with Q2, which is right here. So we'll put 0, minus 1, 1, and then I'll put that scalar out the front. Okay, and then we put Q2 hat, right? Yeah. 0, minus 1, 1. Okay, so we need to now calculate these dot products, simplify those. But notice here, we've got a 1 on root 2 and a 1 on root 2 there, so we can just view that product as 1/2, okay, which simplifies things a little, and likewise here. But let's dot these two things on the inside. So 0 plus 0 plus minus 1. Okay, but we have a minus there, so that becomes plus 1/2 overall, right? So minus 1, 0, minus 1. And then plus 1/2, 0, 1, 1, and I better peek at my notes. Yeah, that looks right. Okay, now this, 0, 0, and then minus 1, but we have a minus there. So again, this is a plus 1/2, and then 0, minus 1, 1. Okay, great. So now we have to add these together. So I can even put a 2 over 2 in the front, right? Just to make this a little bit simple, so I can pull the denominator of 2 out and just add integers if I want to. Okay, so in the top, we've got minus 2. All right, then we have 1, minus 1, 0. Okay, so 0 next. And then we have minus 2 plus 1 plus 1, again, that's 0, and then we have this 1/2. So this is minus 1, 0, 0. All right, so I'll just write this in the corner. Q3 is minus 1, 0, 0. All right, and that's already a unit vector, isn't it? So we can even just put the hat on it straight away. Okay, good. So we've got all of those vectors, Q1 hat, Q2 hat, Q3 hat. Now we need to put those together into our orthogonal matrix Q. So I hope I can do that here on this page. And so let's see, I've got a lot of 1 on root 2s. So I think I can even put that out the front, right? So let's do that. Put that out the front there. And then I can just write the integer entries. Okay, so looking up here, 0, 1, 1, so 0, 1, 1, Then the next one, 0, minus 1, 1. Okay, great. And now this one, I need to introduce a root 2 in there in order to make it cancel with that 1 on root 2, because I've chosen to avoid the root 2's in the other entries. So we need to put a minus root 2 there and a 0, 0. Okay, great. So now we have our orthogonal matrix, and you can take dot products between the columns here and see that those dot products are equal to 0, which tells you that yes, they're at least orthogonal to one another as vectors, right? And so it looks like it's plausible that it could be correct. I think it's correct. Okay, so let's move on. I guess that took me a little bit long. So the next one, which is rather simple. Okay, so I've rewritten this a little bit, right? Because here we've got this in the language of M and Q times M, but I just wanted to keep it self-contained here. So it's the very same problem, just different letters. Okay, so I've worded it. Let B equal to Q1 times Q2, where Q1 and Q2 are orthogonal matrices. Is this product orthogonal? Okay, and so what we need to do is take, okay, so if it were orthogonal, we would be looking at B transpose B, and we would be hoping, for starters, that that's equal to the identity, because if it is, then we're more or less done, right? We would find that this is orthogonal. Okay, so let's calculate this then. So we have Q1, Q2, and then all transposed, and then times Q1, Q2. Okay, so we have to apply the rule AB all transpose is B transpose A transpose. So we reverse these. There's a Q1 there. So we have Q2 transpose, Q1 transpose, Q1, Q2. And now our multiplication is associative, right? So we can introduce some brackets right here to emphasize that we want to look at Q1 transpose times Q1. Okay, so then we have Q2 transpose, and we know that this product has to be the identity because we know that Q1 is orthogonal. So this is I. And then we have Q2. And of course, I times Q2 is Q2. So this is Q2 transpose Q2. And since Q2 is orthogonal, we get the identity matrix, right? And likewise, if you did B times B transpose, you should get the same thing. Okay, so the answer is yes, B orthogonal. All right, so how are we going in the chat? Everybody content? Any questions? All right, good. So next one, and similarly, I've changed the language with this one too, okay? Because it was written in terms of M and Q, and I'll just show it to you. All right, so consider the 9 by 9 block matrix with diagonal entries Q, M, Q. For each of the zeros is a 3 by 3 matrix of zeros. So what's the inverse of G? Okay, so the way I've written it is like this. So I didn't bother to write the zeros because in mathematics, occasionally you can just do this, leave the rest blank, and it's well understood that there are zeros there, right? But you're still dealing with a matrix. And these are block matrices. Okay, so I'll go with that here. And so we're calculating the inverse, right? So now, but you might suspect what the inverse is straight away because you know that these block matrices inside, that they are orthogonal. And so you would suspect naturally that the inverse of G is the transpose of G. Okay, so let's go with that assumption, but of course we have to prove it. So what we want to calculate is G transpose times G Okay, and so let's just put this in. So then we would be transposing the zeros, right? Sending the zeros over here and vice versa across the diagonal. But that doesn't have any effect on this, right? It's still 0. And likewise, inside these block matrices, when we transpose the entries in those as a 9 by 9, it's the same as if we transpose each of these block matrices. So the transpose of G is equal to Q2 transpose, Q1 transpose, Q2 transpose down the diagonal, right, with zeros everywhere else. Okay, and then we still have G as Q2, Q1, Q2. All right, and now we just multiply. Okay, so this works the same way as if these are just entries of a 3 by 3 matrix. So what we can do then is say that this product is Q2 transpose times Q2, and then we've got zeros because we're just multiplying 0 matrices. And down here next we have Q1 transpose times Q1, and then Q2, whoops, put the 2 in the wrong place. Q2 transpose Q2. Okay, and now you probably already see what's going on, right? That will end up with the identity down the diagonal, and then so we'll put this is I3, I3, I3 because these matrices are orthogonal. Okay, and so we end up seeing that this is I9, right? So the 9 by 9 identity matrix. And so the answer is that G inverse is in fact G transpose. So G inverse is G transpose. G is orthogonal. Okay, any questions about that? Now, if you wanted to go through the calculations with a full 9 by 9, you could, right? Just if you're a little bit in disbelief of the mechanics of this. You might do that once and then never do it again. Okay, so that's the quiz complete now. I don't have much time, but I said to Yoni that if I had a little bit of time, I would talk about polynomials a little bit. Okay, so let's see. I'll just give you a little bit of an overview, because what you'll do next is you'll learn about eigenvalues and eigenvectors. And when you solve those, it comes down to solving a polynomial, right? So if you had matrices with real entries, then you would have a polynomial with real coefficients, right? And the way that we write polynomials with real coefficients is just like this, because so you have an underlying field, right, which is the real numbers, and this is the letter that your variable is, right? So if you've got a polynomial in one variable, you might write it like this, or with another letter, like t, for example, right? And this means polynomials with real coefficients. Okay, so let's briefly consider quadratics. So quadratics. All right, so you've got degree 2. So something like a2x squared plus a1x plus a0. All right, so that's a quadratic. Now you've got a couple possibilities depending on this on the discriminant. So the discriminant of this would be, and I probably should have written ABC, right? Because then I can just say b squared minus 4ac. In fact, why don't we just do this now? So a, b, and call this c, okay? Hope that's not too messy. So the discriminant, let's call it delta b squared minus 4ac. All right, so if this is equal to 0, then you've got a repeated root. So something like, so if delta is equal to 0, then e.g. x minus 1 all squared, right? A repeated root. Yeah, because the thing inside the square root is 0, and so you don't have the plus or minus in your quadratic formula. And incidentally, we may as well write that. So x is equal to negative b plus or minus square root of delta, all over 2a. So this is your quadratic formula, right? So when your discriminant is 0, this part goes away, and so you don't actually have the plus or minus, and so you have the repeated root. So you have a root, but it appears twice. Okay, and so that brings me to the fundamental theorem of algebra, which says that if you have a polynomial of degree n, then you have exactly n roots of the polynomial that are all complex, right? So real numbers are also complex numbers because it's a subset of the complex numbers. So you have n complex roots, but in order to count n, you've got to count repeats like this. Okay, so we would say that this polynomial here has 2 roots. They're just repeated. So you have the number 1 twice. Okay, it's degree 2. You have 2 roots. And they're complex because 1 is a real number and therefore it's a complex number. Okay, all right, now cubics. Now I'll just give you an example. So since we're running out of time, I'll write my brief note, I'll just show my brief notes on this. So cubics, this is a section on cubics that I've got to talk about. Because again, I'm just taking a few words. Okay, so here's an example of cubics with 3 repeated roots. So this one, x cubed minus 3x plus 2. So here we've got repeated roots, x minus 1 squared, but times x plus 2. So there are 3 real roots there. The 1 is repeated twice. All right, now this polynomial here, this cubic, 2x cubed minus 4x plus 5, that has 1 real root and yeah, so basically that one looks like something like this. I can see my pen's running out of ink. So I have to do something about it. I'll get the red pen. I'm going to try to do this again. So it might look like this if you were to plot it, right? And you can see visually it only intersects the axis once in one place. The axis would be up here if it had 3 real roots, okay? But since it intersects the axis in one position, it has 1 real root, and the other 2 roots are not real, but they're complex. And so another thing that I should say is that whenever you do have non-real complex roots, they always come in pairs, all right? So if you have a plus bi as a complex root of your polynomial, say of degree n, then you have a minus bi as well as a root. So they always come in pairs, okay? So this is basically your crash course on polynomials, but you might get on Wikipedia, for example, and just have a bigger crash course on polynomials, okay? Because they're interesting. All right, and so I think I'll knock off there. It's 5:53 p.m., so I think that's good enough. And I'll take a little bit of a break and grab some water, and then we'll start back up again at 6 with Walla. Okay, thank you. And Walla, I'll just leave your quiz sheet up here. Yeah. The timing is all right. Yeah. Sorry. Yeah, it's good. Yeah. Yeah, perfect. Okay, hello, Jonathan, how are you going?
Yeah, good, thanks. Can you hear me?
Let's see if we've got our volume turned up high enough today.
Can you hear me, Sam?
Actually, I
Can
can
you hear me,
see
Sam?
that you've got your mic turned on, but maybe we don't. So, yeah, I think Jonathan, we've got the same issue, and I thought I'd fix it, but apparently I hadn't. Okay, so welcome everyone. So we'll start with Walla. Walla will do questions 1 through 7 on this quiz that you did, and then you'll hear from me, and I'll do question 8, 9, and 10, and then I'll talk about polynomials. Okay, thanks, Walla.
Hi. Let's start with the questions from a quiz. So let's try to find the question 1 up to question 7. At the beginning, we have in the question 1, they ask, consider the vectors v1 minus 1, 0, minus 1 transpose, v2 is 0, minus 1, 1 transpose, and v3 equals 0, 1, 1 transpose. Let the 3 by 3 matrix A have columns v1, v2, and v3. That is, A is a matrix consists of v1, v2, and v3. In part 1, they ask, do the vectors v1, v2, and v3 constitute a set of orthogonal vectors? If they are consist an orthogonal vectors, we need to check. To check that, we need to find an inner product between v1 and v2, v1 with v3, and v3 with v2. Let's start with question 1. So we have 3 different vectors. We have v1 equal minus 1, 0, and minus 1 transpose, v2 equal 0, minus 1, and 1 transpose, and v3 equal 0, 1, 1 transpose. Number 1, to show if they are orthogonal, let's try to find an inner product between v1 transpose times v2. We need to find v1 transpose times v2. v1 transpose equal minus 1, 0, and minus 1. Another product with v2, which equal to 0, minus 1, and 1. If you try to find an inner product between v1 transpose and v2, we will get minus 1 times 0, 0, 0 times minus 1 is 0, and minus 1 times 1, this is equal to minus 1. And this is not equal to 0. So the answer is no. Why? Because v1 transpose times v2 are not orthogonal, because the answer is minus 1, and this is not equal to 0. So the answer is no. So v1 and v2 are not orthogonal. In part 2, they ask, are the vectors v2 and v3 orthogonal? To test that, if v2 and v3 are orthogonal, we need to find an inner product between v2 transpose and v3. In part 2, they ask if v2 and v3 orthogonal. To test if v2 and v3 are orthogonal, we need to find an inner product between v2 transpose times v3. v2 equal 0, minus 1, and 1. Multiply with v3, which equal to 0, 1, and 1. Let's try to find an inner product between v2 and v3. 0 times 0 is 0, minus 1 times 1 equal minus 1, 1 times 1 is 1, and minus 1 plus 1 equal to 0. So v2 and v3 are orthogonal. So the answer is yes, because we get 0. Part 1 and 2 are direct, and we can solve it easily. Okay, this is the solution for part 1 and part 2. In part 3, they ask, execute the Gram-Schmidt procedures on the vectors v1, v2, and v3 in this order. We need to keep this order, v1, v2, and v3. Present the output as columns of an orthogonal matrix, and we need to find an orthogonal matrix Q, which consists of Q1, Q2, and Q3. Let's try find the solution for question 3. For question 3, we need to apply Gram-Schmidt. At the beginning, we need to know what is the Gram-Schmidt. The Gram-Schmidt said Qi tilde equal to Vi minus Q1 transpose times Vi, and all of these multiply with Q1 minus up to reach Qi minus 1 transpose times Vi, and all of these must multiply with the Qi minus 1. So at the beginning, we need to find the Q1 tilde. If you try to find the Q1 tilde, you will get that the Q1 tilde equal to V1. So we need to find the value of the Q1 tilde. The value of the Q1 tilde equal V1. And V1 from the question, this is equal to minus 1, 0, and minus 1. This is not equal to 0, so we will not stop here. We need to find the value of Q1. To find the value of Q1, we need to divide each term in Q1 tilde by the norm of Q1 tilde. So to find the value of Q1, it's equal to Q1 tilde divided by the norm of Q1 tilde. So we need to find the norm of Q1 tilde. Here we have this vector, minus 1, 0, and minus 1. And we need to divide by the norm of Q1 tilde. And the norm here is minus 1 to power 2 plus 0 to power 2 plus minus 1 to power 2, and all of these under the square root. So this is equal the square root of minus 1 square, which equal 1 plus 0 plus 1. We need to divide by square root of 2. So the value of Q1 equal minus 1 divided by square root of 2, 0 divided by square root of 2, which equal to 0, minus 1 divided by square root of 2, which equal minus 1 divided by square root of 2 transpose. So this is the value of Q1, which also Q1, we can put it in the matrix Q capital. Here it's the first column in Q capital matrix. Now let's try to find the value of Q2 tilde. The value of Q2 tilde, if you try to substitute in Gram-Schmidt, you will get Q2 tilde equal V2 minus Q1 transpose inner product with V2 multiply with Q1. This is equal to, the value of V2 from the question is 0, minus 1, and 1 transpose minus. We need to find an inner product between Q1 transpose and V2. And Q1 transpose is calculated here, which equal minus 1 over square root of 2, 0, and minus 1 over square root of 2. We need to find an inner product between Q1 transpose and V2, which equal to 0, minus 1, and 1. And all of these multiply with Q1, which equal minus 1 over square root of 2, 0, minus 1 over square root of 2 transpose. At the beginning, we need to simplify Q1 transpose times V2, because we need to find an inner product between these two vectors. This is equal to 0, minus 1, 1 transpose minus. If you try to simplify this one, minus 1 over square root of 2 multiplied with 0 is 0. 0 multiplied with minus 1 is also a 0. Minus 1 over square root of 2 times 1. This will give you minus 1 over square root of 2. So here we have minus 1 over square root of 2. This constant multiplied with minus 1 over square root of 2, 0, minus 1 over square root of 2 transpose. Now we need to calculate minus 1 over square root of 2 multiply with Q1. This will give you here this vector 0, minus 1, 1 transpose minus. Let's try to multiply minus 1 over square root of 2 with minus 1 over square root of 2. This will give you 1 over 2. minus 1 over square root of 2 times 0 is 0. And the last thing, minus 1 over square root of 2 multiplied with minus 1 over square root of 2 is also a half. Now just we need to subtract v2 from this vector. 0 minus a half, this will give you minus a half, minus 1 minus 0 is minus 1, and 1 minus a half is a half. Transpose. So this is the value of q2 tilde. And the value of q2 tilde also not equal to 0. So we need to continue and find the value of q2. So we need to divide by the norm of q2. Here we have q2 tilde equal to minus a half minus 1 and half transpose. So to find the value of q2, it's equal the vector q2 tilde divided by the norm of q2 tilde. This is equal minus a half minus 1 and a half transpose divided by the norm of this vector. To find the norm, this is equal to square root of minus a half to power 2 plus minus 1 to power 2 plus a half to power 2. This is equal to minus a half, 1 and half to power 2 divided by, if you try to calculate this one, this will give you square root of 6 over 4. If you try to divide 6 by 2 and 4 by 2, you will get square root of 3 over 2. So we need to divide each items from q2 tilde by the norm of q2 tilde, which is here square root of 3 over 2, to find the value of q2. So the value of q2 equal minus a half divided by square root of 3 over 2. This will give you minus 1 over square root of 6. 1 divided by square root of 3 over 2. This is equal square root minus here. This is equal minus square root of 2 over 3. And a half divided by square root of 3 over 2. This is equal 1 over square root of 6. This is the value of q2. So we found the value of q1 and the value of q2. We need to find the value of q3 tilde. To find the value of q3 tilde, we need to apply Gram-Schmidt again. To find the value of q3 tilde, this is equal v3 minus q1 transpose times v3, and all of these multiply with q1 minus q2 tilde multiply with v3, and all of these multiply with q2. Let's try to substitute. The value of v3, it's from the question, which equals 0, 1, and 1, minus q1 transpose times v3, the value of q1 transpose, which equal to minus 1 over square root of 2, 0, and minus 1 over square root of 2. Multiply with v3, which equal to 0, 1, and 1. And all of these multiply with q2, which equal to minus 1 over square root of 2, 0, and minus 1 over square root of 2 transpose. Minus q2 transpose, which equal to minus 1 over square root of 6 minus square root of 2 over 3 and 1 over square root of 6. This is multiply with v3, which equal to 0, 1, and 1. And all of these multiply with q2, which equal minus 1 over square root of 6 minus square root of 2 over 3 and 1 over square root of 6 transpose. At the beginning, we need to simplify, and we need to find the value of q1 transpose times v3, and we need to find the value of q2 transpose times v3. Let's try to simplify from here. If we try to multiply q1 transpose times v3, we need to multiply minus 1 over square root of 2 times 0 is 0, and 0 times 1 is 0, and minus 1 over square root of 2. With 1, it's minus 1 over square root of 2. So from here, you will get just minus 1 over square root of 2. And if we try to simplify here, we need to multiply minus 1 over square root of 6 times 0 is 0, and we need to multiply minus square root of 2 over 3 times 1. This is equal minus square root of 2 over 3. And if we multiply 1 over square root of 6 times 1, this is equal 1 over square root of 6. If you try to simplify these together, minus square root of 2 over 3 plus 1 over square root of 6, this will give you minus 1 over square root of 6. So instead of this one, just we need to write minus 1 over square root of 6. Now let's try to find the value of Q3 tilde. After we calculate the inner product, you will get that Q3 tilde equal 0, 1, 1 transpose minus 1 over square root of 2 multiplied with minus 1 over square root of 2, 0, minus 1 over square root of 2 transpose minus, here we have minus 1 over square root of 6 multiplied with minus 1 over square root of 6 minus square root of 2 over 3 and 1 over square root of 6. Okay, let's simplify. This is equal 0, 1, 1 transpose minus, let's try to multiply these together, minus 1 over square root of 2. With each element here, you will get half, 0, and half, minus, we need to multiply minus 1 over square root of 6 with each element here, you will get 1 over 6, 1 over 3, and minus 1 over 6. Now just we need to subtract these three vectors. 0 minus a half minus 1 over 6. This is equal minus 2 over 3. 1 minus 0 minus 1 over 3. This is equal 2 over 3. 1 minus a half minus 1 over 6. This is equal 2 over 3 transpose. And this vector also not equal to 0. So we need to find the value of Q3 by divide each element by the norm of Q3 tilde. So to find the value of Q3, this is equal Q3 tilde divided by the norm of Q3 tilde. This is equal minus 2 over 3, 2 over 3, and 2 over 3 transpose divide by the norm of this vector, and the norm of this vector equal to square root of minus 2 over 3 squared plus 2 over 3 square plus 2 over 3 square. So this is equal minus 2 over 3, 2 over 3, and 2 over 3 transpose divide by 2 over square root of 3. Just we need to simplify down here. You will get this is equal 2 over square root of 3. Now we need to divide minus 2 over 3 by 2 over square root of 3 and 2 over 3. We need to divide it by 2 over square root of 3 and 2 over 3, the last one, by 2 over square root of 3 to find the value of Q3. So the value of Q3 equal minus 1 over square root of 3, 1 over square root of 3, and 1 over square root of 3 transpose. Now we found the value of Q1, Q2, and Q3, so we can write the matrix Q. So the matrix Q consists of 3 different vectors. Here we need to write Q1 in the first column. We need to write Q2 in the second column and Q3 in the third column. If you look back, the value of the Q1 equal minus 1 over square root of 2, 0, and minus 1 over square root of 2. The values of Q2 equal minus 1 over square root of 6 minus square root of 2 over 3 and 1 over square root of 6. And the values of Q3 is minus 1 over square root of 3, 1 over square root of 3, and 1 over square root of 3. To check if this matrix is orthogonal, you need to multiply any two vectors, you will get 0. If you try to multiply Q1 transpose times Q2, you will get 0. If you try to multiply Q2 with the Q3, also you will get 0. And if you try to multiply Q1 with the Q3, also you will get 0. Because this matrix is an orthogonal matrix, which means that the multiplication of any two vectors is 0. So this is the solution for question 3. So we can find the value of the matrix Q, and we applied Gram-Smith. Is it clear for you? Is it clear for you? Okay. Just you need to calculate a bit of calculation. Okay. In number 4, they ask, determine the value of the Q inverse. We need to find the value of Q inverse. Okay. In number 3, we found that the matrix Q is an orthogonal matrix. And we know if we have an orthogonal matrix, so Q inverse is equal Q transpose. Just you need to say that because Q is an orthogonal matrix, let's apply that Q transpose equal Q inverse. So just you need to find the value of Q transpose, and the value of Q transpose is the same as Q inverse because the matrix Q is an orthogonal matrix. Okay. In number 5, they ask, what is the null space of the matrix A? We need to find the null space of matrix A. In general, we can find the null space if AX equal 0. And if you look back, that we proved that the matrix A consists of linearly independent columns. So the null space in this case is equal 0, and only we have just 0's null space. So because here the matrix A consists of linearly independent columns, so we have null space which equal to 0. Because the matrix A because the matrix A is a square matrix which consists from linearly independent column we show that the matrix A consists of linearly independent columns from Gram-Smith. We prove that from Gram-Smith that it consists from linearly independent columns. So the null space here is 0. So just here we have the null space is 0. So the null space is 0 equals 0, 0, 0 transpose. In general, if you have a linearly independent columns, the null space all the time equals 0. This is a rule. Yeah, is there any question? Okay. Okay. Number 6, they ask, what is the rank of the matrix A? We need to find the value of rank of this matrix. Number 6, they ask, what's the rank of a matrix A? We said before that the matrix A consists of linearly independent columns. To find the rank of this matrix, just we need to count the number of linearly independent vectors in this matrix. And the matrix A consists of 3 different linearly independent vectors. So the ranks of this matrix is 3. So The answer is because the matrix A is a square matrix which consists of linearly independent columns. So the ranks of this matrix equal the number of linearly independent columns of this matrix, and it's equal to 3. Since a matrix A is a square matrix and has an independent columns, so the ranks of a matrix A equal 3, which equal the number of vectors in matrix A. Just we need to count the number of vectors, or the number of linearly independent vectors, which consists the matrix A. Yeah, is it clear for you? Okay, the last thing, and after that you will continue with some. In number 7, they ask, are the vectors v1, v2, and v3 a basis for R3? They ask you if they are a basis or not. Are the vectors v1, v2, v3 bases in R3? Okay. According to the definition of basis, we said that it's a basis if it's a span in R3 or if these vectors are linearly independent. And we showed from Gram-Smith that these vectors are linearly independent. In addition, these vectors also span in R3. So yes, it's a basis in R3. So the answer is yes. Yes, because these vectors v1, v2, v3 span in R3, and they are linearly independent. From Gram-Smith, we proved that. So yes, it's a base in R3. Yeah, is there any question from 1 to 7? Is there any question related to your request from question 1 to 7? Is it clear for you? Okay. Now let's continue with some.
Thanks, Walla. Okay, I'll get myself organized. Now, my blue pen ran out of ink in the last session, so I'm going to use red. It's okay. Well, I'll use red. Well, no, it's okay. I'll use red. Thank you. Well, I know you don't have any illness, but I like to use pens I've been using for some strange reason. I'm a little bit strange. Okay. Right. All right, guys, so let me just shift the chat if you can. The wrong mouse. Okay, so Walla, would you mind if I borrow that page again? Thank you. Okay, so I'm going to talk to you about questions 8 through 10 here, and then we'll talk a little bit about polynomials. So the first one we'll do together, question 8 says, now execute the Gram-Schmidt procedure on the vectors v3, v2, and v1 in that order. So in order 3, 2, 1. Present the output in columns of an orthogonal matrix M. Now I'm going to change the name of the letters, right? Just for some reason I didn't want to use the letter M. So I've written this in my own way here. All right, so I say run Gram-Schmidt on these 3, but they're taken from above, just so you know, in the top here. All right, and I've just written them as columns rather than rows transposed. So here they are, and straight away I just call them A1, A2, and A3 so that I don't get confused when I use this formula. And secondly, I've decided not to use the tilde over the top as I think Walla was using. And so I'll compute this, and then I'll have to take the norm of it and divide by that norm. And so I'm calling the ones that I have divided by the norm already Q with a hat on the top, right? So just to mean that they're unit vectors. Okay, so given that, let's get busy and start to calculate this. So we'll first note that in the sum, when we put in I equals 1, we've got nothing in the sum, right? Because this says sum from k equals 1 up to 0 in the case that I equals 1. And so that's actually nothing because the top is less than where we start, right? And so that's the convention here. So put I equals 1, the case we'll look at first. Okay, and then so this just says that Q subscript I is equal to AI and then minus 0, which of course just AI. Okay, so this is 0, 1, and 1. And now straight away we can take the norm and divide by that norm and get the unit vector Q1 with a hat on it. Hang on, I meant to make a 1 there rather than I's. Okay, so great. So Q1 with the hat on it is just 1 on root 2, and I like to put that out the front. Okay, 0, 1, 1, because the norm of this is the square root of 0 squared plus 1 squared plus 1 squared, which is root 2. And so dividing by that, we have our unit vector there. Okay, great. So that one's done. And now let's have a look at I equal to 2. So when I is 2, now we have one thing in our sum there. And so we can write that Q2 is equal to A2 minus A subscript 2 dot product with Q1 with a hat on it, and then Q1 with a hat on it there. Right, so I'm taking dot products here in my formula, but of course you can do this with matrix products, right? You just transpose the first one, multiply by the second vector, and that's the same thing as taking the dot product. Okay, so now that we've got the formula written out for the case I equals 2, let's simplify this subbing in. A2 is 0, minus 1, 1. And then we subtract. So in here we have a dot product or scalar product, and then we'll be multiplying by this vector. Okay, so I'll put in the 0, 1, 1. But now I'm just going to note that that 1 on root 2, I can put that out the front. Okay, and in this dot product, I also have a 1 on root 2. So noting that, I can just write out in the front as 1/2. Okay, in other words, 1 on root 2 times 1 on root 2 is 1/2. And so I can view this as taking the dot product of just A2, which is 0, minus 1, 1, and then dot, where is it, Q1? Yeah, but I've already pulled the root 2 out the front, so I'll just write 0, 1, 1. Okay, good. So that simplifies things. And then look, we can see what that dot product is. 0 plus minus 1 plus 1, that's 0. Okay, so this becomes this vector minus 0, which in fact is just A2, which is very easy. Okay, and now we take its norm, and we can see that the norm is root 2. And dividing by that, we have Q2 hat is 1 on root 2, 0 minus 1, 1. Okay, great. So that is the case I equals 2 finished. And so far what we have is the first 2 columns of the matrix Q. All right, so proceeding to do the third one. So I equals 3. Okay, so what we do first is simplify our formula so that we have Q3 is equal to A3 minus, now we've got a sum of 2 things because we stop here subbing in I equals 3, that's 3 minus 1 is 2. So we have k equals 1 and k equals 2. Okay, so let's just put these in. So A3 dot Q1 hat, Q1 hat, and then minus A3 dot Q2 hat, Q2 hat. Okay, good. And now we just need to sub in the values. So A3 is minus 1, 0, minus 1. And then we have a dot product here. But again, we've got Q1 hat and Q1 hat here. And they both have a 1 on root 2 in them. So noting that we've got 2 of those and the entries of A3 are integer, so we can take the product of the 1 on root 2 and write that as 1/2 out in front. Okay, good. And now I can express the rest as A3 dot with the integer part of Q1. So 0, 1, 1. And then I'll put the integer part of Q1 hat out here. Okay, good. And then underneath that, I'll put the rest of it. So minus A3 dot Q2 hat and so on. Okay, so with the Q2 hats, we have a 1 on root 2 there as well. Okay, and the A3 just has integers in it. So taking the product of the 1 on root 2s, we have another minus 1/2 in front. And now we can take a dot product of integer entry vectors. Okay, so I'll copy down the integer entries there. So 0, minus 1, 1, and then our dot product 0, minus 1, 1. Okay, and I just need to fill in A3 there. So A3 minus 1, 0, minus 1. All right, good. Now we can just look at that and take our dot product. And so I can see that it's just minus 1 here, because we have zeros everywhere else. And so minus 1 times minus 1/2 there is plus 1/2. Hang on, I better check my notes. Okay, so anyway, I'm jumping ahead of things, so I better write the first here, minus 1, 0, minus 1. Okay, and then again up in here, we've got 0, 0, and minus 1, so that's a plus 1/2, and then 0, 1, 1. All right, and then likewise 0, 0, minus 1 there, and then the minus 1 times the minus 1/2 gives us plus 1/2. That's why I put a plus there. And 0, minus 1, 1. Okay, and so looking at this first one, I want to put a denominator of 1/2 here just to simplify this. So I'll include it now. So 1/2, and I have to change these entries to being minus 2s. Okay, so that's good. All right, now I can factor out the 1/2 and add the integers. And so we get 1/2 of, let's see, minus 2 in the top entry, and then 0 in the second entry, and then minus 2 plus 1 plus 1, that's 0 as well. Okay, and then we can cancel the 2, and we have minus 1, 0, 0. All right, now this is already a unit vector, so we can say that this is also equal to Q3 hat is minus 1, 0, 0. Okay, good. So we have all of our vectors now, Q1 hat, Q2 hat, and Q3 hat. And so now we can put those together, concatenate those into the matrix Q, the orthogonal matrix Q. And now since Q1 hat, Q2 hat, both have a 1 on root 2 in it, I'm going to pull that out the front and write 1 on root 2. And then I'll put the integer entries where I can. But of course, since this Q3 entry doesn't have a 1 on root 2 there, I have to put it in here in the last entry. So I'll do that one first. So minus root 2, 0, and 0. Okay, but the other ones, now I can just write the integer entries there. So Q1 was 0, 1, 1 with the 1 on root 2 out the front. And then Q2 0, -1, and 1 with the 1 on root 2 out the front, and now we're done. And so note that when you take the dot product of any two of these columns within this matrix Q, you notice that that dot product is equal to 0. Okay, so column 1 dot column 2 is equal to 0, and likewise column 1 dot column 3 is equal to 0. Okay, and column 2 dot column 3 is equal to 0. So we see that all of the vectors are orthogonal to one another, right? So we have an orthogonal matrix here. All right, and so let's just note that A equals QR. This is the QR decomposition. So R will be upper triangular, and A is A1, A2, and A3, right? Concatenated just like that. And we can calculate the matrix R by multiplying Q transpose times A on the left. Okay, because the inverse of Q is the transpose of Q when we have an orthogonal matrix. Okay, good. So any questions, Jonathan or Zin Kian? I guess not. Okay, next question then. All good, all good. Great. Thanks, guys. Okay, so this one says, we're looking at number 9 now. Define the matrix B equals Q times M. Is B an orthogonal matrix? Okay, so I've rewritten this a little bit differently. So I'd say let B equal Q1 times Q2, where Q1 and Q2 are orthogonal. Is the matrix B orthogonal? All right, so working with that then, I want to check B transpose B, all right? Because if I get B transpose B equal to the identity, then I know that this matrix B is orthogonal. Okay, so then subbing in, what we have is bracket Q1, Q2 transpose, and then Q1, Q2, which is B. Okay, so we need to use our rule on this. The transpose of the product is the product of their transposes, but in reverse. So we have Q2 transpose, Q1 transpose, Q1, and then Q2. Okay, but let's note, I want to put the bracket around that. Remember, it's associative. I can just do that, as in multiplication is associative. And we're just noting here that Q1 transpose times Q1 is equal to the identity because Q1 is orthogonal, right? And so this is Q2 transpose identity times Q2, all right? And we already see the answer here, Q2 transpose times Q2, because I times Q2 is Q2. And then since Q2 is orthogonal, this is just the identity. Okay, and I don't even know what the size of this matrix is. It doesn't matter, right? So I don't know what subscript to put there. It doesn't matter though. Okay, let's move on to the next question, unless you guys have any questions, but I guess you don't. So the next and last question here, number 10, says, consider now the 9 by 9 block matrix. Okay, so you look at that and you see a 3 by 3, right? But you treat each of the entries as if they're 3 by 3 matrices, and you view this as a 9 by 9 matrix. So here the zeros, you should see those as 3 by 3 matrices full of zeros. Okay, the question says, what is the inverse of the matrix G? So with this one, I've rewritten this in the following way. So consider the 9 by 9 block matrix, Q2, Q1, Q2. What is the inverse of G, where Q1 and Q2 are orthogonal? So you see I haven't written any zeros there, but in mathematics, that'll be understood as the rest of it is zero matrices, or 0 entries, right? And so these are block matrices here. Okay, so great. So now we want to know what is the inverse of G. Doesn't have an inverse. And so you might assume that if well, you obviously suspect probably that this is that this G is going to be orthogonal, okay? So under that suspicion, what you want to do is calculate G transpose times G, okay? Because if you get the 9 by 9 identity matrix, then you're done, right? You know it's orthogonal. All right, so applying the transpose to G, now what we can do here, remember what it does is you can think of it as replacing the rows with columns and columns with rows, right? But alternatively, you can think of it as reflecting the entries about the diagonal. Okay, so if you do that with all the zeros that are here on the left and right side of the diagonal blocks, you're just swapping those, right? You're swapping zeros for zeros, and of course that has no effect. But likewise, what you're doing in here is if you transpose G, you're just transposing the blocks along that diagonal of block matrices. Okay, so G transpose then is Q2 transpose followed by next in the diagonal Q1 transpose followed by Q2 transpose. And then we just have Q2, Q1, and Q2. Okay, good. And so now taking the product, we can just take the product as if this is 2 3 by 3 matrices. In other words, we can take the product of these two matrices here, even though they're 9 by 9, we can take this as Q2 transpose times Q2, and then we've got zeros, right? And then next in the diagonal, we have Q1 transpose times Q1, and then Q2 transpose times Q2. Okay, good. So if you believe that multiplication, and you might want to check, right? And you could check just by filling out a whole 9 by 9. You'd have many zeros, right? You'd have what, at least, do I really want to count this? I don't think so. Let's not count. Okay, so moving on. Taking this product, what we have is, because each of these are orthogonal, so we see that we have the identity matrix there, but it's 3 by 3. We have I3 here, and we have I3 here. Okay, but if you look closely, well, that's I9. All right, so this is I9. In other words, the 9 by 9 identity matrix. So we do see that G transpose times G is the identity matrix, and so we know straight away, since G is orthogonal, that G inverse is equal to G transpose. Okay, so that's the quiz done. Let me have a peek at the time. Okay, it's about 3 minutes to 50, and I reckon I'm probably going to take another 6 minutes. So next, we're going to talk about polynomials, because Yoni will soon talk to you about eigenvalues and eigenvectors. Okay, and so they always involve solving a polynomial. So if you have a 2 by 2 matrix with real entries, then what you end up with in taking eigenvalues is you end up having to solve a degree 2 polynomial with real coefficients. Okay, and it may not have real solutions. So just take basically a crash course on polynomials. So polynomials. So here I've got the description of the set. So this talks about, I mean, technically this refers to a ring, right? So a ring of polynomials. So here we have a field R, so the field of real numbers, and then it says that this is basically the powers of X times real numbers, right? And so that's how you get the elements of this set. So the variable is X in this case, but of course you could put T or some other letter. And so this is the set of polynomials with real coefficients, but we're going to talk about these and their roots. Okay, so let's begin with quadratics. Okay, so what I have here is ax squared plus bx plus c. So that's degree 2, because here we see the 2 is the highest exponent, and so that's the degree of the polynomial. Now I've got the discriminant, which will be probably familiar to you if you went to high school. Okay, so that discriminant is important in classifying what kind of quadratic you have because of the quadratic formula right here. So we have solutions or roots, otherwise called zeros of the polynomial. They're given by this formula, right? And it's very easy to solve this or complete the square and get this formula for the roots of a quadratic polynomial. Okay, so you've got minus b plus or minus the square root of the discriminant, which is b squared minus 4ac, and that's all over 2a. Okay, so now if you had discriminant equal to 0, you would get, for example, this polynomial here, x minus 1 all squared, will have, once you expand it and calculate the discriminant, you'll find that that discriminant is equal to 0. Okay, and we can see that in the way it's written here, x minus 1 all squared, because that root is what we say repeated. So it's there twice. Okay, x minus 1 times x minus 1, and that makes it there twice. All right, so, and you see that here in the formula, because when delta is 0, that plus or minus just vanishes, right? Because it's plus or minus 0, which makes this minus b over 2a. Okay, and so that gives you a repeated root in that case. So that brings me to mention the fundamental theorem of algebra that says that a polynomial, say with real coefficients of degree n, has exactly n roots, provided that you take those roots to be in the field of complex numbers, and provided that you allow those roots to be repeated. Okay, so for example, this one, x minus 1 all squared, has two complex roots because the root 1 is a real root, but the real numbers form a subset of the complex numbers. And so we have the number 1 repeated, and so we have two complex roots, 1 and 1. Okay, so moving on to talk about cubics, and now I have some brief notes already written about cubics here on the next page. So here's some examples of cubics. So x cubed, now x cubed has 3 repeated roots, 0, 0, and 0. Okay, so how about this one, x cubed minus 3x plus 2. So if I factorize that, I get x plus 2 times x minus 1 squared, and so we have 3 complex roots. Those roots are minus 2, 1, but the 1 is repeated, and so 2 of those roots are repeated. Okay, and now 2 other examples would be 2x cubed minus 4x plus 5. So this one has 1 real root and 2 non-real roots, and the other 2 non-real roots are complex roots, of course, and they come in pairs. Okay, so whenever you have a polynomial that has a complex root that it's not real, it comes in a pair, a plus or minus bi. Okay, so if you have a plus bi as a root of your polynomial of degree n, then you know that a minus bi is also a root of the same polynomial. Okay, so let's have a look at the geometry quickly. And so what I've roughly plotted is 2x cubed minus 4x plus 5. Okay, so here we can see it intersects the x-axis in one place, but there are 3 complex roots. So this one here is real, right? But here you can see it's only going to intersect once. So the other 2 roots of this polynomial here are complex, and they come in pairs, right? So it'll be of the form a plus or minus bi. All right, now if we just shifted the axis like that, then we might be talking about this one right here. So 2x cubed minus 4x plus 1. Okay, now this one, so shifting the axis to put the x-axis there, now I'm talking about 2x cubed minus 4x plus 1. Now we've got 3 real roots. And so 1, 2, 3, that equals the degree there. They're all real, but they're also all complex because the real numbers form a subset of the complex numbers. Okay, so again, fundamental theorem of algebra is satisfied there. All right, so I think that's all I need to say. Other than, well, no, I don't want to jump ahead of him, so I'll let Yoni talk about eigenvalues and eigenvectors. Okay, so that's all. Thanks, guys. I'll see you next time. Let me know if you got any questions now. Okay, thank you and good night. Thanks, Jonathan. Thanks, Qian.